Hello, welcome to the class. Um, Today we are going to start section 1.4, which is titled as the language of graphs. You know the textbook of this course. The textbook is Susan Eep, Discrete Mathematics with Application. What you need is the fifth edition. This is from Cengage Learning. You have to get the web assign access to do homework. Once you get the web assign access to do the homework, you will get the electronic version of the textbook free. So that is the cheapest option available for you. If you would like, you can get the hardcover book, which is expensive. Um, you can do the first homework with the trial version of WebAssign. After you can decide to pay. All right. So this course covers three chapters from the textbook. Um, the first the first chapter in this course is the 10th chapter of the textbook, and then the second chapter of this course is the 11th chapter of the textbook, and the third chapter of this course is the 12th chapter of the textbook. um, in the first chapter in this class, that is the 10th chapter of the textbook, we are going to cover six sections. That goes like 10.1, 10.2, 10.3, blah blah blah, up to 10.6. This section is 1.4, which is kind of an introduction to graphs. So here we learn some technical information about graphs as the introduction. All right, so let's go forward. This is the language of graphs. Chapter 1 of the textbook is speaking mathematically. Section 1.4, language of graphs. And then let's read this. Imagine an organization that wants to set up teams with three to work on some projects. So they have to set up teams. Each team consists three people. Okay, so they have to work on the projects. In order to maximize the number of people on each team who had previously experienced working together. So the target is they have to make the group such that the group consists people those already work together. All right. So the main thing that concerns here is the prior teamwork. Okay, the prior teamwork, whether they have been in a team prior to this project. All right. The director asks the members to provide names of their previous partners. Okay, so here you have the names of people, and then here you see the partners of each person. Those are the previous partners. All right. Now you can put this in a graph. Let's see. This is Anna. Where's Anna? Anna's here. So here you have Anna, and then Anna worked with Dan and Flor. Dan is here, Flor is here, so you can connect Anna with Dan and Flor. All right, so you connect Anna with this person and Anna with that person because they work together. And then go to Bill, which is here, who is here, and Bill work with Kai, Flor, and then Hal. All right, so that's about a Bill. And then give me, so I will just use a different color. So let me mark the same color with the same vertices. And then thirdly, I'm choosing Chi, who work with Bew, and then Flo. All right. So like that, you can make a graph. You can make this structure that explains which one work with which one. All right. So this is something very easy. So you can get this structure. You can get this structure from this table. All right. Then go down. From the diagram, it is easy to see that you can see that Bew, Kai, and Flo are a group of three previous partners. Okay, let me consider that group. Bew, who's right here, and then Kai, who is right here, and then Flo. So these three were in a group in olden days. All right, so that makes a nice group because all three work together. So this will be your first group. Okay, so because they three work together, it is given right here. Bew, Kai, and Flo are a group of three previous partners, and so it would be reasonable to make them from one of. It is reasonable for them to form one of these teams. Okay, so these three people make a team. Give me a second. All right. Now you can just take these three people out and just find out the rest. So the rest goes like this. Here you have Hi. Here you have Ira. Here you have Gia. They are connected. And then here you have Anna. And here you have Ed. Ed is connected with Hi. And then Ed is connected with Dan. And then Dan is connected with Anna. So these are the remaining people, all right? Since you have taken these three people out, you have taken Ben, Kai, and Flo out. Okay, so these are the remaining people with the connections, all right? Okay, so this is the diagram below shows the result when these three names are removed from the diagram. So this is the case when you remove these three people from the diagram. All right. I'll go down. This drawing shows that placing Hi on the same team as Ed would leave Gia and Ira on a team where they would not have previous partners. So this is what we have. Now you have to make the second and third group. All right, so you have to make groups of three people. What happens if you put Hi and Ed in the same team? You put Hi and Ed in the same team because they are connected by an edge. So you can put them in the same group. If you put them in the same group, what will happen is these two people will be separated. Okay, Ira and Gia. So they have to work in the same group. All right, so that is disadvantage. Why? Because they have never been in the same group, Ira and Gia. So that means putting Hi and Ed in the same group is not meaningful. Okay, putting Hi and Ed in the same group is not meaningful. So like that you can decide which group is more meaningful than the other. All right, so what I would do, so I will put I will put, give me a second. I will put hull with gear and era. Okay, so that means these three, I take these three people into one group. Okay, so that is the second group. If I take these three people into one group, so these three people make the third group. Okay. This is group 3. This is group 2. So let me mark group 1. This is group 1. Alright, so this way we can make groups. Making group was very easy because you are given this nice structure. All right, it was very easy because you are given this nice structure. All right, so let's read this slide. Such illustration of a structure is known as a graph. Now we are coming to the most important definition, which is called a graph. Okay, such illustration, this illustration is called a graph. All right, the dots are called vertices. All right, so what are the dots? Here are the dots. These are called vertices. Okay, so these are vertices. The dots are called vertices. The plural of that one is vertex. And the line segments joining vertices are called edges. Okay, let me mark the line segments. These are the edges. Okay, now you know the meaning of a graph. Okay, that's the definition of a graph. So these are the edges. As you can see from the drawing, it is possible for two edges to cross at a point that is not a vertex. That means here you see, let me use a different color. Here you see this, this edge crosses that edge. Okay, so this I mark them in yellow. So this edge crosses that edge at this point, but that is not a vertex. Keep that in mind. Okay, so sometimes there are edges which are crossing each other, but they are not vertex. Okay, so keep that in mind. If it's a vertex, then you have to mark it as a dot. It is possible for two edges to cross at a point that is not a vertex. All right, go forward. Now there's another thing you have to understand. These are graphs, of course, but there's another type of graph you just learn in calculus, maybe Calc 1. Graph of a function. You learn graph of a function, but here it is not that. This is not graph of a function. All right. So if I just tell what is a graph of a function, it is something like this. So you have a set of values here. Let me use a different color. So here you have a set of values which is called the domain. All right. Let's say these are the values in the domain. Let's say this is 0, +1, 2, -1, -2. There are 3 values in the domain. Okay, let's say in the range you have, domain has 5 values. In the range you have 3 values, 0, 1, 4. Okay, now you can understand what this function is. Okay, so here you have domain, here you have range. Okay, now there's a function from here to here which is called f. Okay, let's say your x is the domain, so this function is, the range is known as f of x. Okay, this range is known as f of x. Okay, this function is actually f equals x square. All right, you are familiar with this function, f equals x square. That is different than graph that we talk here. This function is called a graph. Okay, so this function right here, then I'm going to draw the graph of this function. Let me take this into a spacious place somewhere here. Okay, now what I'm going to do, I'm going to graph this. So I have this f of x-axis, I have this x-axis, I have -1, -2, 1, 2. So the values are 1, 2, 3, 4. When x is -1, the corresponding value was 1. When x is -2, the value is 4. When x is 0, the value is 0, and that is there, and that is there. So this is the corresponding, let me not connect them. So this is the corresponding graph. This point to that point to this point to that point to that. Alright, so if you need, you can connect them. So this is also called a graph, which is different from the graph that we learn here. Alright, so go forward. Now we're going to understand some definitions. These are formal definitions in graphs. All right. A graph G consists of two finite sets, non-empty set V of G. Actually, this V stands for vertices. Okay, non-empty set Vg of vertices and a set E of G. This is for edges. All right. Let me underline these two words. Where each edge is associated with a set consisting of either one or two vertices called endpoints. All right. So there are endpoints. If it's an edge, like this, so there should be two vertices. There should be two vertices at the start and at the end of the edge. Okay, so this is the start. That is the end. So these are vertices. That is the edge. So these are vertices. So these are vertices. Okay, that's explained right here. The correspondence from edges to endpoint is called the edge endpoint function. So I'm gonna you are going to learn edge endpoint function later. So that's a function which gives you the relationship between edges to endpoints. Okay, it gives a relationship from edges to endpoint that we're going to learn very soon. Let me write, this is not clear, vertices. All right. An edge with just one endpoint is called a loop. If it has one endpoint, then it's called a loop. So how can edge has one endpoint? So edge is kind of something like this, or maybe that's an edge. So it should have one endpoint. Normally it has two endpoints. In this special case, it has only one endpoint. So then the shape should look like this, starting from this vertex and coming back to the same vertex. Okay, so this is called a loop. Okay, and two or more distinct edges with the same set of endpoints are called parallel. That means that should have the same endpoints. It's something like this. So start here. Sorry, I'm using different color. Start here, and there. So there are three edges like that. So they are called parallel. So here you have vertex 1, here you have vertex 2, and here you have two edges. Okay, they are called parallel. Let me write as edges are parallel. Okay, these edges are parallel. Okay, then an edge is said to connect its endpoints two vertices that are connected by an edge is called adjacent, and a vertex that is an endpoint of a loop is called to be adjacent to itself. Now we are going to learn something new, another technical term, which is adjacent. All right, an edge said to connect its endpoints. Two vertices that are connected by an edge are called adjacent. Okay, so you have two vertices. Let's say vertex A and vertex B. Vertex A and vertex B. If there's an edge, then you say A is adjacent to B. Then you say if this happens, you say A is adjacent to B. There's another technical term which is called adjacent. Okay. Then vertex that is an endpoint of a loop is said to be adjacent to itself. All right. So now you have an edge. Now you have an edge like this, and then it has a loop. So you say A is adjacent to A. This is a special case. Okay, it's a loop. You say A is adjacent to A. All right. Let me take this right word. Let me put a divider. It's a divider. All right. Then we're going to learn another technical term, which is incident. An edge is said to be incident on each of its endpoints, and two edges incident on the same endpoint are called adjacent. Okay, so this is the case that we're going to discuss. So you have an edge Okay, so we have an edge. Let's say this edge is maybe V, and here you have A, the vertex. You say edge of is okay, that's V. You say edge V is incident to A. If this happens, you say edge V is incident to vertex A. All right. So all these are technical terms. So you can learn this when you proceed. Okay. A vertex on which no edges are incident is called an isolated vertex. Okay. Now this is again something important. So there's an edge. So there's a vertex like this. There's a vertex. So no edges are incident to this. No edges are incident to that. All right. So that means no edges are joining with this vertex. Okay, such a case is called an isolation. Okay. So this is an isolated vertex. Okay, all these are technical terms, so you can learn them later if you do not understand, or you can read it later. All right, so go forward. And then we're going to learn some terminology. This is an example where we learn the terminology that we have already learned. Consider the following graphs. You have two graphs. One graph here, another graph over there. All right, let's move to the first question. Write a vertex set and the edge set. You have to write the vertex set, edge set, and give a table showing the edge endpoint function. There are three things you have to find. All right. So first thing, second thing, third thing. All right. In the problem B, find all edges that are incident on V1, all the vertices that are adjacent to V1, and blah blah blah. Okay, let's do the first problem first. Okay, you have to find vertex set in each case. All right, you have to find vertex set. First write the vertex set. Now I'm gonna tell you something. I don't know whether you learn set theory. This is called set. Theory. Okay, I don't know whether you learn set theory. This is a mathematics course. Sometimes students enroll into, which is called set theory. Sometimes you learn set theory from some other classes. Since you have taken discrete math 1, you have learned set theory, a little bit of set theory in discrete math 1. In set theory, we learn about sets. All right, we learn about sets and all the technical information about sets. All right, so that we have covered in discrete math. If it is a set, you have to represent set inside curly brackets. You know that, inside curly brackets. Okay, so if it's a set, let's say A is a set, then you have to represent the elements of A inside curly brackets. Okay, let's say it is, my set consists three colors: red, blue, and green. All right, so this is a set. That's a set. I have to make sure that I put this curly bracket and I have to close it by another curly bracket, and I have to separate them by commas. All right, so these are the rules in set theory that you have learned in discrete math 1. So some students are doing weird things when they write sets. I have to make sure that you do not do such weird things. Those weird things include sometimes students put dash to separate elements. That's wrong. All right, you can put dash. Or people put some other weird things like semicolon. That's also wrong. You have to put a comma. That's the standard. Or for these curly brackets, some students put square brackets. That's again wrong. Or maybe parentheses. That's again wrong. Okay, they should be curly brackets and then they should be commas. All right, keep that in mind when you write sets. Okay, now vertex set, I just put equal sign and then start of a curly bracket, and what are the vertices. All right, so this is a vertex, that's 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 a. There are 7 vertices. I'm sorry, I made a mistake. This is an edge. This is an edge. Okay, so there are. There's another vertex right here. Okay, so vertex are the dots. How many dots are there? There are 6 dots. So the vertex set includes V1, V2, V3, V4, V5, V6. And then I have to close by a curly brackets. And then you have to write the edge set. Edge set consists that. All these are edges, all right? So again, start with a curly bracket. My curly bracket is weird, I'm sorry about that. So this is a curly bracket. And then write them E1, comma, E2, comma, E3, comma, E4, comma, E5, comma, E6, comma, E7. All right, so these are the edges. So there are 7 edges and 6 vertices. So these are the vertex set and edge set. Now we move forward. We have to find edge endpoint function. Edge endpoint function. All right. So this is the edge endpoint function. All right. In edge endpoint function, first column should be edges, and then you have to mention endpoints as vertices. Okay, so these are the edges, and then you have to write endpoints. Let me put like edge and then end points. Okay, so the first edge will be E1 and then E2 and then E3 and then E4 and then E5 and then E6 and then E7. All right, so these are the edges, and then we have to find endpoints. If you take E1, the endpoints are for E1, endpoints are V2 and V1. Okay, so you have to write the endpoints in curly brackets again because that's a set. v1 comma v2. And then if you take e2, where's e2? Oh, yeah, right here. If you take e2, the endpoints are v1 and v3. v1 comma v3. And if you take e3, those are v1 and v3 again. Okay, and if you take e4, v2 v3, and if you take e5, it is v5 v6, and if you take e6, it is v5. Okay, let me go to that, which was e6 right here. e6, you can see e6 is a loop, so it has only one endpoint. Okay, it has one endpoint, which is v5. Now go to e7. e7 is again a loop, so it has only one endpoint, so it is v6. Even if it has one endpoint, you have to put this curly bracket, otherwise it is wrong. v6, right? v6. Right, so that is the solution for part A. Now we just move to part B. Okay, part B says find all edges that are incident on V1. Just catch up V1, catch V1, that's V1. So what are the edges incident on V1? Those are E1, E2, V3. Okay, so this is the solution. They are E1, E2, E3 are incident on V1. Okay, and the next case is all the vertices that are adjacent to V1. Catch V1. It is right here. Okay, so all the vertices are adjacent to that. So this vertex is adjacent to that by an edge E1. And again, this vertex is adjacent to that, to V1. So there are two vertices adjacent to V1. Okay, they are V2 and V3 are adjacent to V1. Okay, the next part. All edges that are adjacent to E1. Get E1, which is right here. The edges adjacent to E1. So what are the edges connecting to this edge? So this edge is connecting to that edge is connecting to this, that edge also connecting to this. So there are three edges, which are E2, E3, E4. E2, E3, E4. All right. So then the next part is all loops. It's clear it has two loops, loop 1, loop 2. Okay, the loops are E6 and E7 are loops. And then all parallel edges. What are the parallel edges? You can see this edge is parallel to that edge, E2 and V3. E2, E3. Okay, and then all vertices that are adjacent to themselves. What vertices are adjacent to themselves? If there's a loop, then it is adjacent to itself. Okay, so it is v5 and v6 because there are some loops. And finally you have to find all isolated vertices. So what is isolated? Which is v4, which is v4. So we have completed part B. Now, this is a good example because this example covers all of the definitions that we learned right here. Okay, it covers all of the definitions that we learned right here. So that example is a very good example. All right, so go forward. All right, now we are going to the next example. Okay, so this example is about um, labeling a graph. Okay, it's a matter of labeling a graph. Example 1.4.3 in your textbook, labeling drawings to show they represent the same graph. This is a very good question. Why this is a very good question? Same graph can be represented to you in different ways, so you will be confused. All right, so you will be confused. So if I give you these two graphs, and I ask, are they similar? Are them similar graphs? Or maybe are them equal? So most of the students will say, no, they are not equal. That's your answer. Most of the students answers, no, they are not equal. That's wrong. They are equal. These are similar graphs, the same graph. All right, so they are equal. Actually, they are equal. But the way it is presented, you are confused. All right, that's all about labeling the graph, labeling and how do you draw that graph. It's all about labeling and drawing. Okay, so that's what we're going to learn here. Consider two graph. Consider the two drawings shown in figure 1.4.1. Do them represent the same graph. Okay, so this your answer. I don't know what your answer is. So most of the students will say no. Okay, now let's learn this little bit. Imagine putting one end of a piece of string at the top vertex of figure 1.4.1a. So you take a string now. Okay, now what you say, you take a string and you're going to lay down the string on this star-shaped graph. You take the string, this is the start of the string. Let me use a different color. Highlighter is good. Alright, so you take the string and you start from here. Oh, that's too wide. How do you make it less wide? All right. All right, good. So let me take them out. So what I'm saying is I'm just laying a string. I'm starting from here. I lay down a string like that, and then lay down like this, and lay down like that. The same string, okay? Lay down like that, lay down like that, and then finish. Okay, so this is the start and end. Start equals end of the string. All right, now what you do, you can just tie up here. This is string, so you can just tie up right here, and then you tie up here and then just you lose it. You just tie up here and then you just rearrange the string. You can just put the string like this. Now string should look like this. Okay, so then you can just turn this string such that you will get this shape. Okay, no, that is, you don't have that star pattern anymore. What you have is a pentagon. Okay, the shape is a pentagon. It's not a star anymore. So then that graph is same. The graph is same. This graph is same as that graph. All right. This is a matter of representing the graph. It's a matter of drawing and labeling. That's what confused you. All right. So that is explained right here. Imagine putting one end. Imagine putting one end of a piece of a string at the top vertex of figure 1.4.1a. Okay, so you call this as vertex 1. Then lay in the string to the next adjacent vertex on the lower right. Call this vertex v2. Then line it to the next adjacent vertex on the upper left. That means v3 and so forth. Returning to the final to the top vertex. That's what we have done here. Okay, we have done that laying down task right here. So we laid down that string. All right. So then go forward. Call the first edge E1, the second edge E2, and the fourth edge E3, and so forth. All right. So this is what we have already learned. So we start. So this is small change. So the start. Give me a second. Give me a tiny bit. So this is not to start and end. Otherwise you will be confused. Let me mark start and end dash right at the top. So this is the start equals end of the string. Okay. String start equals end. So that is right here. Why I mark that? Why I changed this start and end? Because you might be confused. Below diagram is little bit different than what I have drawn here. To avoid that confusion, I just change this start and end. All right, so go to this. So the same thing that we have done previously. So start from here. You go down like that, going like that, going like that, going like that. All right. So now you mark, label the vertices and edges. So you mark all the vertices and label vertices and edges. Okay. Now go to the next slide. Now imagine picking up the piece of string together with its labels and repositioning it as follows. Okay. So you took the string up and then you just turn the string around and reposition it. All right. The shape of the string will look like this now. It's a pentagon. Now the new shape that you get is a pentagon that we have discussed already. It's a pentagon, and then these are the edges. You could mark this as V1, V2, V3, V4, V5, and then you have to put the edges. What is the edge between V1 and V2? Which is E1. So this is E1. And then between V2 and V3, the edge is E2. And then between V3 and V4, the edge is E3, E4, and E5. All right, so this is what you get, the pentagon. All right, so they are similar. Now your conclusion is both graphs are similar. All right, so keep that in mind. Graphs can be labeled in a confusing way. You might misunderstand they are two graphs, not the same graph. All right, go forward. Now we are moving to another example. You can use graphs to represent networks, which is the most important application. All right. So you all are computer. I mean, in this class, most of them are computer science students. I know that because I taught this class several times. Most of them are computer students. So you are familiar with networks, internets, all right, or intranet like local nets. Okay. So all these are actually graph structures. Graphs. When I say graph structures, you might think like computer graph structures that you learn in your course catalog. No, not that graph structure. It's a structure of graphs. All right. As an example, just consider airports and the flights. All right. All the airports can be represented as vertices. If a plane flies from one airport to another airport, then you can mark those, you can connect those two airports by an edge. Okay, let's say there are three airplanes going from Houston to Dallas every day. So then you can mark three parallel edges between these three airports. Like that, you can just represent all the airports in this world as a graph. All right, all the airports are in this simple graph. So you can find out if, let's say, you have to go to Beijing in China. So you can find out the shortest path because you have this graph. Okay, so shortest and the fastest route. Okay, you start from Corpus Christi, then go to the nearest airport, Houston, and then from Houston you might go to Dubai. Okay, or maybe from Houston you might go to California, and from California all the way to the Beijing. Or maybe you go to Dubai and then from Dubai to Beijing. All right, so all those are graphs. Those are graphs that are used to represent networks. Like I explained you before, some computer networks like social networks. Social networks are networks, those are graphs. All right. So the learning graph theory is very important for computer science students. Not only computer science students, but also for math students and also for other students. All right, because their life is mostly about networks. All right. So there are some examples here: telephone, electric power, gas pipeline, and air transportation system can be represented by graphs from small local area networks to global internet system that connects millions of computers worldwide. Actually, they are not only computers. There might be Internet of Things, like all the instruments that can be connected by using the internet, like the printers. Okay, your printer, office printer, university printers, and then computers, hand phones, and all the devices that are using the internet, like security cameras, they are also using internet, or maybe credit card devices, scanners, everything. Okay, internet of things. All right, so you can understand internets are learning graph theory is very important because they are, of course, the internet. All right. Questions that arise in the designing of such system involve choosing connecting edges to minimize cost or optimize certain type of service and so forth. All right, so let's say you have this network, or let's say you have this graph. Now the next question is your target. What's your target? If you are going, if this is about airports and flights, then your target is to go to the destination fast, the fastest route, or maybe the shortest distance. Shortest distance is not always the fastest. Keep that in mind. Okay, either you can go to use the shortest distance or the fastest route, or maybe some other factors like less number of stops. There's a route that has less number of stops, things like that. Okay, so your objective might be different. Sometimes you might minimize the cost. If you're driving your car between cities, then if your concern is the fuel, then you have to make sure that you minimize the cost. Okay, so this is what is explained here, which is very important. So another network, a typical network called hub and spoke model is shown below. Okay, so it has hubs. These are hubs. Okay, and then it has spokes. Okay, it has spokes. All right, so this network is called hub and spoke network. All right, so just to give you the name, I'm not going to talk too much about that hub and spoke model. All right, now just talk about directed graphs. Okay, there are two types of graphs mainly: directed graphs and undirected graphs. Okay, the undirected graphs are the graphs that we have learned so far. Undirected graphs are the graphs where the direction is not important. All right, like friendship. Friendships, if you consider friendship network, that is actually an undirected graph. Let's say you have these people, John. Okay, this is Scott. All right, this is Mary. So they are friends, and then this is George. Okay, so Mary is a friend of George, and Mary is a friend of John, and John is a friend of Scott. John is a friend of George, and then that's it. Okay, so this is the friendship network. So it doesn't matter whether it has arrows or not, because this is a friendship network. Arrow is not important. So this is called a undirected graph. Okay, such a graph is called an undirected graph. Undirected. These are called undirected graphs. Okay, now let's talk about directed graphs. In directed graphs, actually, there should be arrows. Okay, so here, there, there, there. Let's say John, Scott, and then Josh, Mary. All right, now think about a directed graph. This might be texting. Okay, John texted Scott, or maybe emailing. John emailed Scott and John emailed Mary. Mary emailed Josh and Mary emailed Scott. Okay, and then Scott emailed Mary. All right, so this is called a directed graph because the arrow is important, the direction is important. This says John texted Scott, not the other way around. And John texted Mary, right, not the other way around. Between Scott and Mary, Mary texted Scott and Scott texted back to Mary. Things like that. Okay, so there are directed networks and undirected networks. There are actually two different fields. Science is sometimes science is different, very different between directed graph and undirected graphs. Okay, so far we refer to undirected graphs. Okay, now let's talk about directed graph. Directed graph is like an undirected graph, except that each edge is associated with an ordered pair of vertices rather than set of vertices. They are ordered pair of vertices. Ordered pair of vertices. Order means there should be a direction. There should be direction. Okay. Direction is important. Direction is important. All right. Thus, each edge of a directed graph can be drawn as an arrow going from the first vertex to the second vertex of the ordered pair. All right. Now let's talk about directed graph a little bit more. Directed graphs, this is the short name for that, digraph, consist of two finite sets. A non-empty set Vg of vertices and non-empty sets dg of directed edges, where each edge associated with an ordered pair of vertices called endpoints. If edge is associated with the pair Vw of the vertices, then E is said to be directed from V to W. Okay, let's say you have this E is associated with the pair VW. Okay, associated with VW. That means E runs from V to W. Okay, so the arrow is important. E runs from V to W. Arrow is important. All right, so that's explained right here. Right, go down. Now let's move to an example. Example 1.4.6 on your textbook. Using a graph to represent knowledge. Okay, which is very important. So you learn artificial intelligence in your curriculum. All right. Sometimes you learn this artificial intelligence, especially computer students are learning artificial intelligence. All right. In many applications of artificial intelligence, knowledge base of information is collected and represented inside a computer. Okay, people are thinking about artificial intelligence, like machine learning, right? So they have to make the computer to think like human beings. All right. So the machine learning is a big field nowadays. All right. So let's say you are making a system like this. You are making an automated system to recognize cats and dogs. Okay, so you train your model. Let's say you have a model, so you train the model with known cats and known dogs. So you train the model many times for the model to understand the features of dogs and features of cats, and then what you do is you test. Okay, training is gone, now you test. Now you just pass a dog to the system, so the system will pass a number. Let's say if it's a dog, then it should pass a small number. If it's a cat, it should pass a big number. Okay, so let's say the number varies from 0 to 1. If it is less than 0.5, then there's a cat. If it's greater than 0.5, there's a dog. So things like that. That's a knowledge system, artificial intelligence. All right. So this is very famous nowadays, artificial intelligence. All right. So the computer is not limited to retrieving data in the same form as it was entered. Okay, so you enter data in one form, but you can retrieve it in a different form. Because of the way the knowledge is represented, and because of the properties that govern the artificial intelligence program. Okay, so the computer is not limited, let me mark this. The computer is not limited to retrieving data in the same form as it was entered. In my dogs and cat example, the data you fed are the images. Okay, you feed the images of dogs and cat. What you get is a number between 0 and 1. This number tells whether you input a dog or a cat. Okay, something like this. All right, so go forward. It can also derive new facts from knowledge base by using certain built-in rules of inference. Okay, statistical inference is very important. Okay, making decisions. Okay, making decisions. Making decisions. All right, so let's move to the example with details. There's a directed graph. Okay, this is like a tree actually. The directed graph shown in figure 1.4.2 is a pictorial representation for simplified knowledge base about periodic publications. Okay, this graph is about periodic publications. There are different types of periodics. Okay, they can be papers, motor trends, newspapers, sport magazine, printed writings. Okay, newspapers can be Suburban Weekly, Big City Daily, and scholarly journals can be long words. Those are having long words, and literary journals, scientific journals. There are a lot of categories for periodics. Okay, so this is a detailed classification of periodics. Okay, so it has a lot of information. Okay, let me take this out. So the question is this: according to this knowledge base, what paper finish does the New York Times use? So now the question is about New York Times. Okay, the question is about New York Times. So it asks you what paper finish this New York Times uses. Okay, first of all, you have to catch up New York Times. This is New York Times. All right, so we have to find what paper finish. Okay, so this is kind of the end of the one of the end of this graph. So you have to go up. So New York Times is an instant of Big City Daily. Okay, you start from here, you go up. That called instant of Big City Daily, and from Big City Daily you go up. Is a newspaper. Big City Daily is a newspaper. Okay, the newspaper paper finish is matte. Okay, so that's how you move. Let me mark it. You start from here. New York Times, and then it's instance of Big City Daily, and then is a newspaper. Paper finish is matte. All right, so that's how you move. Here, go down. All right, so let me read this now. The arrow going from New York Times to Big City Daily labeled instance of. Okay, that's what we learned right now. From New York Times to Big City Daily is named as instant of. Shows that the New York Times is a big city daily. Okay, New York Times is a big city daily, which we have discussed already. The arrow going from big city daily to newspaper labeled is a shows that a big city daily is a newspaper. Big city daily is a newspaper. The arrow going from newspaper to matte is a matte finish, paper finish. Labeled paper finish indicates that the paper finish on a newspaper is matte. Hence, it can be inferred that the paper finish of New York Times is matte. All right, so that is the answer for the solution. That's the answer for the question. This is the question, that's the answer. All right, so go forward. Now we have another example. Okay, before that example, let's learn about degree of a vertex. That's another important thing, degree of a vertex. Let G be a graph and V is a vertex of G. The degree of V, denoted by dig V, equals the number of edges that are incident on V with an edge that is a loop counted twice. It is something like this. So you have a vertex which is V, and then you have to count how many edges incident to that. Edge 1, edge 2, edge 3, edge 4. Okay, so dig of V equals 4. All right, the next case, one edge here, one edge here, one edge here, and there's a loop. Okay, then this, let's say this is W. Degree of W is actually 5 because loop is counted twice. Okay, loop is counted twice. There's an example. Find the degree of each vertex of the graph G shown below. All right, so there are how many vertices? 1, 2, 3. There are 3 vertices. Degree of V1. Okay, no edges adjacent to this. Give me a second. Okay, no edges incident to this, so the degree is 0. Okay, so the reason for that is since no edge is incident on V1. Okay, so it is isolated. This is, let me mark that this is isolated. This is called isolated vertex. All right, so degree of V2, there are 2 edges, so the degree of V2 is 2. Since both E1 and E2 are incident on V2, and degree of V3, one edge, one edge, one edge, one edge, because the loop is considered as 2 edges. All right, so the degree of this one is 4. Since E1 and E2 are incident on V3 and the loop E3 is also incident on V3. All right, so then there are four edges incident on the vertex V3, so the degree is 4. So that's end of the section from next day we can start the next section. So thank you very much. um, I hold office hours during the class time, so you can just watch this video during class time. If you have questions, then stop by. So I'm available online. Thank you very much. Have a nice time.